This is packet number 25, problem number 8, and we're looking at composition of functions and the chain rule. So part A says we want to find b of t, which is the composition of the function b and s of t. So we have b of s is e to the s, and we have s of t is t squared. So b of s of t, I need to substitute in the t squared into, there's an s on b of s, so just e to the t squared. In order to find the derivative of b with respect to s, well, b is a function of s already. So the derivative of b with respect to s is e to the s. The derivative of e to the s would just be e to the s. And for the function s of t, which is t squared, s is a function of t, so ds dt is just 2t. Now it says find the derivative of b with respect to t. Well, from part A, we found that b of t can be e to the t squared. And so the derivative of b with respect to t is e to the t squared. And then we have to multiply by the derivative of the exponent, which is 2t. So with part E, thinking about the fractional derivative notation, how can we relate those two fractions? Well, if I think about putting those three fractions together, how could I mathematically make them somehow be an equation? Well, if I take dB dt, it's equivalent to dB ds times ds dt. Strictly looking at the fractions, our ds in the denominator and our ds in the numerator would cancel one another out, and I'd have dB dt equals dB dt. So this form, dB dt equals dB ds times ds dt, is a second form of the chain rule. So on part F, we want to find dB dt when t is 4. Well, we have dB dt we found in part D, and to evaluate that at 4, we'll just be substituting in 4 for the t. So I'd have e to the 16th times 8. Usually we have the constant in front, so 8 times e to the 16th. Likewise, I could put in the -3, and I'd end up with -6 e to the 9th. Same idea on h.